Alright, the next question is given x1 of n is equal to sequence 1 1 1 and x2 of n is another sequence 1 2. Find the convolution of the sequences graphically. So the question clearly mentions to do this or analyze this graphically. So there is no need of or no option of doing the tabular method. So let's remove it graphically. So the convolution summers, what you are required to evaluate is y of n is sigma over k equal to minus infinity to plus infinity x of k into h of n minus k. You are required to evaluate this equation. For that, you must have x of k within your hand and h of n minus k at our hand. Obtaining x of k is very simple. We have x1 of n. Okay, so here the question is about x1 of n and x2 of n. So I would overwrite this equation accordingly. So okay, since it is x1 of n and x2 of n, the equation would be sigma. The equation would be x1 of k into x2 of n minus k. Okay, so you should be ready with x1 of k and x2 of n minus k. Obtaining x1 of k is very simple because x1 of n is given. You just change the index to k. But for obtaining x2 of n minus k, what you would go through is you have x2 of n. So find x2 of k simply by changing the index. Then find x2 of minus k and then x2 of n minus k. And you would be remembering how to obtain x2 of n minus k. It is just shift this x2 of minus k by n units. If n is negative, shift n units to the left, and if n is positive, shift n units to the right. That's the procedure. Okay, we have done many problems like this in the previous videos. Okay, so I think I will increase the pace slightly. Okay, I think you can follow it. So initially I'm going to draw x1 of k. Okay, this is x1 of k with index k, and 1 1 1 are the amplitude sample values at 0 1 2. In the question there is no any arrow marks given, so I think we can take default the first sample at n equal to 0. Okay, so now I have got x1 of k on the board. Next attempt is to draw x2 of k, right? x2 of k, then x2 of minus k, and then find x2 of n minus k accordingly. Alright, this is x2 of k over k, because this is at k equal to 0, this is at k equal to 1, and amplitude at k equal to 0 is 1, and at k equal to 1 it is 2. So this is x2 of k. Now what is the next step? You have to find out or draw x2 of minus k. Okay, to find x2 of minus k from x2 of k, just fold this signal about the y-axis. Okay, so this sample at k equal to 0 remains itself. Okay, remains there. But what about this sample? This sample at k equal to 1 falls to k equal to minus 1. Okay, so x2 of minus k comes like this, right? Now next procedure is to draw x2 of n minus k. But before that, you need to be clear about how many samples of the output signal are we going to evaluate. Okay, from what value of n to what value. Okay, so how can you find out the initial sample of y of n, or initial sample n value of y of n? I have already instructed the procedure. The starting value of y of n will be the sum of the starting value of x of n and the starting value of x2 of n. Starting value means I'm not indicating the amplitude, but n value, starting n value, time value of x1 of n plus starting time value of x2 of n. At what n does x1 of n start? I think I will indicate as n1. So x1 of n starts at n1 equal to 0. Okay. Similarly, x2 of n also starts at n2 equal to 0. So what should be the starting value of y of n? N will be n1 plus n2, which is equal to 0. So we have to start finding y of 0. Okay, from this equation. Okay, then y of 1, y of 2, etc. And what should be the end value of y of n? And n value of y of n? It should be the sum of end n value of x1 of n plus end n value of x2 of n. So what is the end n value of x1 of n? This is n equal to 0, this is n equal to 1, this is n equal to 2. Okay, so end n value of x1 of n is 2. Okay, similarly, what is the end n value of x2 of n? This is at n equal to 0, this is at n equal to 1. Okay, so n equal to 1 is the last sample, is the last index of x2 of n. So we have to find out the end value of y of n and n value of y of n, which is 2 plus 1, right? 2 plus 1 equal to 3. So we have to find out up to y of 3. Okay, up to y of 3. So these 4 samples we have to evaluate. Okay, so as a first step to it, let me write the expression. So the first sample to be obtained is y of 0. Okay, so from this equation, what is y of 0? Put n equal to 0, right? Y of n, y of 0 can be evaluated from y of n by putting n equal to 0. So in the LHS, as it is a function, as we have put a 0 for n, for wherever you find n in the RHS, that also should be made to 0. Okay, so sigma k equal to minus infinity plus infinity x1 of k into x2 of 0 minus k, which is actually x2 of minus k. Okay, so this is the first expression you need to evaluate to obtain y of 0. So in order to evaluate this equation, you must have x1 of k with you, that is already here. Okay, and x2 of minus k also should be with you, that is here, x2 of minus k. For convenience, I can redraw this x2 of minus k aligned to the x1 of k for better understanding. Okay, I have drawn x2 of minus k right below x1 of k in an aligned manner, where its n values are aligned. Okay, fine. Now the equation to evaluate y of 0 clearly tells us to find x1 of k into x2 of minus k initially. Okay, so x1 of k into x2 of minus k means you have to multiply sample wise. Okay, here there is only one sample in each of this that get multiplied, because all other will be 0. The sample multiplied by 0, these two samples by multiplied by 0. Okay, so we have only this sample at n equals 0. So x1 of k into x2 of minus k, you will get one sample, only one sample as 1 into 1. Okay, here the amplitude is 1, here it is 1, so 1 into 1 is 1. There is no other samples to summate. There's a summation here that is valid only if you have multiple samples as the product. So here the answer is 1. So we got y of 0 equal to 1. Okay, I can write it somewhere for the final consolidation. Y of 0 equal to 1. Okay, next our aim is to find out y of 1. Okay, so we have to make necessary changes in the equation. Okay, so y of 1 that we need to evaluate, y of 1 from the parent equation, y of 1 should be sigma x1 of k into x2 of 1 minus k. You're replacing n with 1. Okay, so I can change it as y of 1 is equal to sigma k equal to minus infinity x1 of k into x2 of 1 minus k. Okay, so this equation clearly asks us to find out what x1 of k multiplied by x2 of 1 minus k. For that, x1 of k should be with us, that's right here. And x2 of 1 minus k, that is not with us, but we can derive it. Okay, this is x2 of minus k. How will you find out x2 of 1 minus k? Just simply shift x2 of minus k to 1 unit to where? Left or right? Right. Okay, 1 unit to the right, because 1 is a positive value, n is 1, is a positive value. Okay, so let us shift x2 of minus k 1 unit to the right. Okay, so I have drawn x2 of 1 minus k, x2 of 1 minus k by shifting x2 of minus k 1 unit to the right. So the sample at minus 1 with a value 2 is at n equal to 0, right? The sample is at n equal to 0, and this sample will be at 1. Okay, this sample is at 1, right? So x2 of 1 minus k we have drawn is correct. Now let us look at the equation. Equation tells us to multiply x1 of k and x2 of 1 minus k. So what will be the result? There are two samples to multiply. This sample multiplied by this sample, you will get 2 into 1. Okay, and this sample with this sample, 1 into 1, and the equation asks us to summate both this product. Okay, so first of all, 2 into 1 is 2, plus the sample 1 into 1 is 1. 2 plus 1 equal to 3. So y of 1 is the next sample of the output, which is 3. You can write it there for consolidation. Y of 1 equal to 3. Okay, so y of 1 is over. We have evaluated y of 1. Next is y of 2. So to obtain y of 2, I can make these two changes. Y of 2 will be equal to sigma over k from minus infinity to infinity, x1 of k into x2 of 2 minus k. So x1 of k is with us here, and x2 of 2 minus k. How will you obtain x2 of 2 minus k? We just look at x2 of minus k, shift it 2 units to the right. Okay, 2 units to the right. Obviously x2 of 2 minus k is x2 of minus k shifted 2 units to the right. So this sample occurs at n equal to 1 or k equal to 1, right? Okay, so let us get back to the equation. We have to find out y of 2. That is, first you have to multiply x1 of k into x2 of 2 minus k and summate all this sample, all the products. So what is x1 of k into x2 of 2 minus k? We have to multiply 1 into 2, okay, plus 1 into 1. Okay, so the result is 1 into 2 plus 1 into 1, which is equal to 2 plus 1, that is 3. So we got y of 2 as 3. I can write it here. Y of 2 is equal to 3. That is our third sample. Okay, is there any more sample to find? Yes, of course, the last final sample, which is y of 3. How will you find out y of 3? Y of 3 can be found out by making necessary changes in the parent equation. So y of 3 will be sigma x1 of k into x2 of 3 minus k. And how will you evaluate or plot x2 of 3 minus k? You shift x2 of minus k 3 units to the right. Okay, 3 units to the right. Okay, this is x2 of 3 minus k. As you can see, this is x2 of minus k shifted to 3 units to right side. Okay, now let us evaluate y of 3 from the equation. That is, you find the product of x1 of k and x2 of 3 minus k, which will give you to multiply this sample with this sample alone. No any samples are left, because all other multiplication will give you 0. So the answer would be 1 into 2. Okay, that is equal to 2. So y of 3 is equal to 2. Okay. Okay, so that was the final sample to obtain. Any other sample you need not evaluate, because it would end up you in 0 as the answer. So let us consolidate the result. Therefore, y of n is equal to sequence 1, 3, 3, 2. Or else, if you want to plot it or sketch it. The question didn't say to plot it, but if you want, you can plot it very simply. Okay, y of 0 is 1. I think I can evaluate, or so y of 0 is 1, then y of 1 is 3, y of 2 is 3, and last sample y of 3 is 2. Okay, 1 3 3 2. This is y of n. It's the final answer. Okay, the next question. For an LTI system, the unit impulse response is given by h of t equal to e raised to minus at u of t, where a greater than 0. Obtain the step response of the system. Okay, so in questions like this, if it is an LTI system, deliberately the output will be the convolution of the input as well as the impulse response. So here in this question, impulse response is given, okay, but where is the input? The input is not given, but there is a hint that obtain the step response of the system. Okay, what do you mean by step response? For beginners, step response is nothing but response of a system to step input. Okay, response or output of a system to step input. Okay, so the input is hidden there. Input is nothing but step input. Okay, so the x of t is given by u of t. Okay, x of t equal to u of t is hidden in the question by the word step response. Okay, so you got x of t equal to u of t, and h of t is given as straight away it is e raised to minus at u of t. And now what you have to obtain is y of t, which is given by the convolution of x of t and h of t. Okay, so there is actually another method by using Laplace transform to obtain the answer very swiftly. Anyway, I would start with the convolution, because we are actually going through the modules dealing with the convolution and LTI systems. Okay, so as per the procedure, the first signal I got to draw is x of tau, which is u of t. Okay, as per the procedure, first you have to draw x of tau. Okay, x of tau, then h of tau, then find h of minus tau, and then h of t minus tau for t very less than 0. Okay, why we are doing this? Because we are now going to realize the convolution integral equation, which is given by y of t is equal to, we have to expand this equation, that is minus infinity to plus infinity, x of tau into h of t minus tau d tau. Okay, x sort of should be found out, h of t minus t tau should be found out. For that, first you draw h of tau, then h of minus tau, and then h of t minus tau. Okay, then I'm going to draw x of tau. X of tau is nothing but the step input. Okay, x of t equal to u of tau t, so x of tau is u of tau. Okay, so this is our x of tau in the index tau 0, and the amplitude is 1. Fine. Now we have to draw h of tau. Okay, h of t is equal to e raised to minus at u of t given in the question. So h of tau will be equal to e raised to minus a tau d tau, I mean u of tau. Okay, e raised to minus a tau u of tau. Okay, and that will be the multiplication of e raised to minus a tau with u of tau. That will give you this signal. Since a is greater than 0 given in the question, this is a decaying exponential signal, which is only right sided because it is being multiplied by u of t in the question. Okay, so this is h of tau. but we need not find h of tau, or we did not stop at h of tau. We have to find out h of minus tau. What is h of minus tau? This is the time folded version of h of tau. So time folded version of h of tau means this will be h of minus tau. Okay. Again, you are not stopping at h of minus tau. What you have to find is h of t minus tau. Initially for t very negative. Okay, h of t minus tau is obtained from h of minus tau by shifting h of minus tau to t units, as you know, t units. But since t is assumed to be large negative initially, h of minus tau should be shifted to the left side. Okay, left side. So I think I could draw like this. Okay, so this is t 0. This 0 is shifted or added with t. T is negative, so this end will be t. Okay, the amplitude will be 1 here. Okay, so this is h of t minus tau for t very less than 0. Okay, now what will be the result of this equation, parent equation? Y of t equal to minus infinity infinity x of tau multiplied by h of t minus tau. X of tau is here, multiplied by h of t minus tau will give you 0. Okay, so initially y of t is equal to 0 because the signals do not overlap anywhere. Okay, now what we do is we increment t so that this entire signal moves towards the right. It moves and on, but still the product is 0. But this product continues to be 0 until this t reaches 0. Okay, so we can boldly write y of t equal to 0 until t less than 0. Okay, so this is the first condition of our output. Okay, so what is the next condition? Next condition is, as you can guess, the signal is shifted towards the origin, and after t greater than 0, what happens? This signal h of t minus tau overlaps with x of tau. Okay, I can draw that condition. Okay, this is such a condition. Okay, t is greater than 0. Now this h of t minus tau gets overlapped with x of tau. Okay, so what is this condition? How can we express this condition? This condition is nothing but very simply, very easily, we can write it as t greater than or equal to 0. Okay, so this is the condition, the time condition or time interval in which we are going to evaluate y of t. Okay, now what is y of t? Therefore y of t in this interval, okay, y of t is equal to integral, this is the parent equation, integral minus infinity to plus infinity. First of all, you have to check whether we need to integrate it from minus infinity to all the way plus to infinity. Now is the answer, because the two signals overlap only between 0 and t. Okay, in all the other time intervals the product is going to be 0, so only between 0 and t the two signals coincide. So the integral, the limit of the integral is from 0 to t. Okay, 0 to t. Then from the equation, next is x of tau. Okay, x of tau. What is x of tau? X of tau is clearly 1. Okay, clearly 1. So 1 into x of tau is 1 into. Next is h of t minus tau. What is h of t minus tau? Actually, h of t, I can write it here. H of t is given in the question as e raised to minus at into u of t. Okay, u of t is now not needed because u of t, the effect of u of t is actually incorporated to trim the signal in one axis. Okay, so h of t is actually equal to e raised to minus at. Now what is h of t minus tau? We have h of t minus tau here, right? So h of t minus tau is replace t by t minus tau. So e raised to minus a into t minus 2. Okay, so x of tau into, instead of h of t minus tau, I can write e raised to minus a into t minus tau d tau. Okay, now we can simplify this as integral over 0 to t e raised to minus at into e raised to plus a tau d tau. Okay, actually the integral is in the dummy variable tau, so we can take e raised to minus at as a constant, take it as outside the integral, 0 to t e raised to a tau d tau, which will give you e raised to minus at into e raised to a tau by a within the limits 0 to t. Okay, that makes you conclude to e raised to minus at by a into, putting the limits, e raised to at minus 1. Okay, so I can take e raised to minus at into the bracket, which will give you e raised to minus at into e raised to at. I can write it e raised to minus at into e raised to at minus e raised to minus at whole by a. This is going to be 1, right? This term is actually 1. So the answer is, final answer is 1 minus e raised to minus at whole divided by a. What is the interval? T greater than or equal to 0. Okay, so our output has two conditions. I can write it here. Y of t is equal to 0 when t is less than 0, and 1 minus e raised to minus at by a when t is greater than or equal to 0. Okay, or in other words, in a single line, actually we can represent this signal in a single line instead of two conditions as y of t is equal to 1 minus e raised to minus at by a into u of t multiplied by u of t is giving you the same meaning as this thing. Okay, so this is the final answer. In this context, I can give you a very simple method to evaluate the integral. Okay, there is an alternate method to this, very simple method. Here actually from the question it is clear that we are to obtain output y of t, we are convolving u of t with h of t. Okay, u of t with h of t, and h of t is given by u of t convolution, h of t is given by e raised to minus at u of t. So there is a result that any function, right, this is a standard result, any function f of t convolved with u of t will give you integral over minus infinity to t that function f of t data. Okay, integral minus infinity to t that function, which function is being convolved with u of t, that function. Okay, so applying this result over here, I can write it as u of t, y of t is equal to u of t convolution e raised to minus at u of t will end up in this result, integral minus infinity to t, which is the other function here. It is e raised to minus at u of t, so e raised to minus at u of t dt. Okay, so this is going to give me, that is equal to, here actually this is a multiplication of e raised to minus at with u of t, which truncates the signal from 0 to infinity only, or 0 to t only. So I can rewrite this limit as 0 to t. Instead of minus infinity to t, the signal is only from 0 to t. So 0 to t e raised to minus at dt. Now no need to write u of t because its effect is here by truncating the limit. Okay, e raised to at dt, that is equal to e raised to minus at by minus a within the limits 0 to t, that is minus 1 by a into e raised to minus at minus e raised to 0 is 1, or this is 1 minus e raised to minus at by a into u of t. Okay, this is the same result we have obtained by this long method. Okay, this is the same result, right? All right, and apart from these, there is yet another simple method to obtain the output. I can give you an alternate simple method to evaluate this by using Laplace transforms. Laplace transform is a very strong tool, very powerful tool to obtain the output of an LTI system. Given x of t equal to u of t, therefore you know the Laplace transform of the input x of s is equal to the Laplace transform of u of t is 1 by s. You know that's 1 by s. Okay. And also given h of t equal to e raised to minus at u of t. Therefore, Laplace transform of h of t is given by h of s is equal to 1 by s plus a. These are standard results. You know this. Okay. And we know y of s is equal to x of s into h of s. Okay. Which will give you 1 by s into 1 by s plus a. Okay. This is equal to 1 by a into 1 by s minus 1 by s plus a. Okay, that's actually given by partial fraction method, but this is a simple partial fraction, I can guess it. Okay, so this is y of s. Okay, this is y of s. And what is y of t? Y of t is the inverse Laplace transform of 1 by a into 1 by s minus 1 by a into, or you can keep 1 by a outside the bracket. Okay, outside the bracket, that will be simple. So 1 by a into 1 by s minus 1 by s plus a, which is equal to, I can take 1 by a outside the inverse Laplace transform due to linearity property, and that will give you 1 by a into L inverse of 1 by s minus L inverse of 1 by s plus a. That gives you straight answer 1 by a into L inverse of 1 by ss. You can see here it is u of t minus L inverse of 1 by s plus a is it is e raised to minus at u of t. That's the answer. This is equal to 1 minus e raised to minus at into u of t whole divided by a, which is the same result as we have obtained in the previous two alternate methods. Okay, let's jump on to the next question. What are the three differences between discrete time sinusoids and continuous time sinusoids? Find the fundamental period of x of n equal to cos pi n if periodic. So this is a combination of theory question and a numerical question. First, let us answer the theory question. What are the three differences? They have asked only three differences between discrete time sinusoids and continuous time sinusoids. So let's start with the differences. I can write continuous time sinusoids here and discrete time sinusoids here. Okay. The first point I would like to notice, in continuous time sinusoids, amplitude is defined. Amplitude of the sinusoid is defined for all value of t. All value of time. Okay. But in discrete time sinusoids, the amplitude is defined only for discrete values of t. Amplitude is not defined for all values of t, but discrete values of t, right? We call it n. Okay. Then the second point is a continuation of first point. The time axis is denoted in t. Time axis in t, but in discrete time sinusoids, the time axis is in n. Okay. The third point turns out to be the question is about continuous time sinusoids. Okay, so a continuous time, standard form of a continuous time sinusoid is x of t equal to a sine omega t plus phi. Okay, this is the standard representation of a continuous time sinusoid, whereas in discrete time sinusoid, the standard representation is x of n equal to a sine omega n plus phi. Okay, here omega is the angular frequency, phi is the phase shift, a is the amplitude, And in discrete time case, A is the amplitude, omega is the digital angular frequency, and phi is the phase shift. Okay, now I can put up another point. In continuous time sinusoids, integration is applied at appropriate contexts. Integration is applied at appropriate contexts, like in finding power, energy, etc. Right? Energy of sinusoid is integral minus infinity infinity more a square sine square omega t dt. Right? You remember this? Okay. But in discrete time sinusoids, instead of integration, summation is used. Summation is used. As in the case of energy, it is sigma n equal to minus infinity to infinity a square sine square omega n. Okay. And now I can point out one more distant point, which tells you that this continuous time sinusoids, if at all they are obtained, if at all a continuous time sinusoid is obtained, they are from natural sources. Natural sources. You could be knowing that analog sensors like temperature sensors, pressure sensors, these are all giving us continuous time values. So if at all any of these sensors are giving a sinusoidal signal, that will be continuous. Okay, but in the case of discrete time sinusoids, these are obtained, if at all obtaining, they are from digital sources or obtained by sampling continuous time sinusoids. That's the only method of obtaining discrete time sinusoids from continuous time sinusoids by a process called sampling. Okay, that is the first part of the question. And there is one more part which asks us to find out the fundamental period of x of n equal to cos pi n. X of n equal to cos pi n. This is a very simple question, very simple indeed. You are given x of n is equal to cos pi n. Okay. First, we need to find out if it is periodic. For that, to check whether this discrete time sinusoid is periodic, you find out omega. Omega is nothing but the coefficient of n inside this cosine term. Okay, that is pi. So omega is equal to pi. Now find omega by 2 pi. So pi by 2 pi will give you a ratio of integers. If it is a ratio of integers, then it is periodic. So it is periodic. Okay, and now that it is periodic, you have to find out the fundamental period. Omega is equal to pi. We have observed omega as pi. Therefore, n is equal to 2 pi by omega, which is equal to 2 pi by pi, which will give you 2. Okay, this 2 is an integer number, so we can stop here and claim that 2 samples is the fundamental time period of the signal. So that completes the answer. Okay, so we will do the next problem. An LTI system is described by y of n minus half y of n minus 1 equal to x of n. Assuming initial conditions as 0, find its impulse response. So you are given a difference equation. This is a difference equation. And initial conditions are 0. You have to find its impulse response. Impulse response is h of n. So applying Z transform will be a very simplest method of solving this problem. Z transform. Okay. You know what Z transform is? Okay. You need to know what Z transform is. Also, the time shifting property of Z transform. Time shifting property of Z transform. What does it say is, if x of n is having a Z transform x of z, okay, if x of n is having a Z transform x of z, then a time shifted version of x of n given by x of n minus n0 will be having a z transform z raised to minus n0 into x of z. Okay, so this is time shifting property. If you know these two, you can simply very easily solve this problem. So let us rewrite the difference equation. Y of n minus half y of n minus 1 is equal to x of n. Okay, now you take z transform on both sides. Apply z transform on both sides of this equation. So what is the z transform of y of n? It is y of z minus half into what is the z transform of y of n minus 1? We need to apply this time shifting property, and as a result you'll be getting z raised to minus 1 into y of z. Okay, that will be equal to, what is the z transform of x of n? It is x of z, right? Now from the LHS we can take y of z common. Y of z into 1 minus half z inverse will be equal to x of z. That will lead to y of z by x of z is equal to, I can take x of z to this side and this factor to this side, denominator. That will give you 1 by 1 minus half z inverse. Okay, and if you have an intuition about transfer function, because in the question it is given assuming initial conditions are 0. So transfer function is defined as the z transform of output divided by z transform of the input, provided all the initial conditions are 0. So we can we can reach to the transfer function concept here. So y of z by x of z, this ratio is called transfer function h of z. Okay, transfer function h of z. Therefore h of z is equal to 1 by 1 minus half z inverse. Okay, now what is the inverse z transform of capital H of z? What is the inverse z transform of this quantity? That will give you impulse response. Therefore h of n is the inverse z transform. This is inverse z transform of h of z. That is equal to inverse z transform of 1 by 1 minus half z inverse. That is a standard result. Okay, that will give you half raised to n u of n. So this is h of n. Okay, that is the answer. All right, let's see one more question. Given h1 of n equal to u of n, h2 of n equal to u of n plus 2 minus u of n, and a third one, h3 of n equal to del of n minus 2. Find the overall impulse response of the given system. So if you have gone through the properties of convolution, there are some points which tells you that if two blocks h1 of n and h2 of n are in parallel, right? If two systems, block means two systems, this is input, this is the output. If two systems with impulse response h1 of n and h2 of n are in a parallel, then we can replace these two systems with an equivalent single system like this, single system h of n. Okay, where h of n is given by adding the individual impulse responses. H of n equal to h1 of n plus h2 of n. Okay, that's one point. Then if at all two systems with impulse response h1 of n and h2 of n respectively are cascaded, then these two systems can be replaced by a single equivalent system h of n, where h of n is given by the convolution of the individual impulse responses. Okay, so h of n equal to h1 of n convolved with h2 of n. Okay, so if you have these two ideas, these 2 points, then it's very simple to solve this problem. Okay, in this problem the systems h1 of n and h2 of n are in parallel. Okay, and the combination or the equivalent of this h1 of n and h2 of n is in cascade with h3 of n. Okay, so I can draw like this: x of n, h of n is equal to h1 of n plus h2 of n is the equivalent of the parallel system. Okay, that is being cascaded with h3 of n to give y of n. Okay, is that clear? Right, so we can proceed. So what is this h of n? H of n is equal to h1 of n plus h2 of n. h1 of n and h2 of n are given in the question. h1 of n is equal to u of n. Okay, u of n from the question, plus h2 of n is given by u of n plus 2 minus u of n. Okay, u of n plus 2 minus u of n. Okay, so you can cancel u of n and minus u of n. That will give you h of n is equal to u of n plus 2. Okay, now x of n, then u of n plus 2 is the h of n. h of n equal to u of n plus 2. This is in cascade with h3 of n. h3 of n is given by del of n minus 2. Okay, to obtain the output. Now what is the equivalent of h of n equal to u of n plus 2 cascaded with h3 of n equal to del of n minus 2? The resultant is the convolution between these two individual responses. So the total response ht of n is equal to u of n plus 2 being convolved with del of n minus 2. Okay, now you need to remember one more result, that any signal convolved with del of n gives that signal itself. Okay, impulse function or impulse signal is like an identity operator in convolution. And also x of n minus n0 convolved with del of n minus n1 will give you x of n minus n0 minus n1. Okay, so from this result you can conclude ht of n, which is the overall impulse response, as u of n plus 2 minus 2, which is equal to u of n. So u of n will be the overall impulse response of this total system. Okay, that's the final answer.